Hey, welcome back to your favorite technical mathematics class. We're going to look at scientific notation today. So let's start out here. These are some examples of some very large or very small notation or numbers. If you have some very large or very small, I should say, if you have extreme magnitudes of numbers, that's when sorry, that's when scientific notation comes in handy. So notice the distance of the Earth is however many, what is that, 149 billion, 400 million kilometers, right? You could say that much easier with scientific notation. Or the world's fastest computers can perform a single calculation at .000, whatever that is. Again, scientific notation would be less cumbersome than that. So let's look at that 149 billion, 400 million distance of the Earth. And we could put that into scientific notation. So scientific notation is anything p times 10 to the k, where you notice your p's got to be less than 10, but it's got to be greater than or equal to 1. Okay, so for this 149 billion, 400 million, what we got to think about is we got to say, well, another way to write that would be some number times 10 to the what would express that in this scientific notation. And this first number right here has got to be between 1, greater than or equal to 1, but less than 10. So it's going to be a single digit. Right now your decimal's right here. Oh, come on. There you go, right there. So I got to think, well, how many times am I going to move this over? 1, 2, 3, 4, 5, 6, 7, 8. That's where I want it. Put the decimal, 1.494 times 10 to the 8th is the same thing. Now I put this in scientific notation, 1.494 times 10 to the 8th. In other words, 1.494 times 10 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 times 10, 8 of those 10s, is 149 billion, 400 million. Okay? So you got to think about when you're, where am I going to put this decimal if I'm moving this thing, right? So here's some more examples. 420,000. 420,000. Right now the decimal's right there. We want it to be between the 4 and the 2. So how many times are you going to move out? 1, 2, 3, 4, 5. So it's going to be 4.2 times 10 to the 5th. And if you're not sure, just check it. You have 4.2 times 10 to the 5th. That means you're going to move that thing 10 to the 5th. You're going to move it right 5. Positive 5 tells you're going to move that thing right 5. 1, 2, 3, 4, 5. Boom, right there. Is that right? Yeah, that's 420,000. Okay, there's that next one. 2 billion, 10 million. Right now, decimal's right here. 1, 2, 3, 4, 5, 6, 7, 8, 9. You want it right there. 2.01. How many times do we move it? 9 times. And again, move that positive 9 says move it back right 9. Let's see if you can have the same number. Sure do. What about the other way with this 0.000052? Notice there's the decimal right there. Okay. So we want to put it between the 5 and the 2, so it's 5.2. So how many times are you going to move it? 1, 2, 3, 4, 5. Now notice we went the other way, so it's going to be negative 5. So this is saying, if you want to check this, move it left 5 to check it. You always check it from scientific notation. 5.2, left 5. 1, 2, 3, 1, 2, 3, 4, 5. There we go. 0.000052, right? Because what this is saying is 5.2 times 10 to the negative 5th. That's 1 over 10 to the 5th. In other words, 5.2 times 1 is 5.2 divided by 100,000. is that 0.00052. Okay, but in scientific notation, again, count to where you got to move it. How about that 0.0108? Where are you going to put that? 0.0108. Got to put it right there, 1.08. Got to move that over twice. So 1.08 times 10 to the what? We moved it twice, -2. Because we got to move it left 2 to get back to what we started with, right? So times 10 to the -2. All right, I actually think these ones might be easier where you're going from scientific to ordinary. So 4.2 times 10 to the 5th. So this is saying just go right 5. Because we're multiplying this thing by 100,000. It's like 4.2 times 100,000. So take that decimal, right 5. 1, 2, 3, 4, 5. 420,000. Next one, which way are you going to go? -11, left 11. 7.12 times 10 to the -11, left 11. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Seven, 1, 2. There it is. Next one, you're going to go right 3. 8.04 times 10 to the 3rd, right? Right 3. It's a positive 3. 1, 2, 3. 8,040. Now your decimal's right there. Last one, 0.24. Whoops, 2.24 times 10 to the -5. -5. You're going to go left 5. You took that 1, 2, 3, 4, 5. Alright, well, adding and subtracting with scientific notation, I prefer to just put it in your ordinary notation first and then add them. So like that first one, you got 2.2 times 10 to the 3rd. 2.2 times 10 to the 3rd, so you're going to move that 1, 2, 3. So you got 2,200. Then you got 5 times 10 to the 3rd, so you're going to move that right 3. So you move it over right 3 and you got 5,000, so you got 2,200 plus your 5,000, 7,200. That's how I'd approach those. Same thing on the subtraction there. 0.0056 times 10 squared. So you move that right 2. 0.56 is what that becomes. And this is minus 2.8 times 10 to the -3. Well, the -3 is going to move that left 3. And you moved it from here to 3 over. So 0.56 minus 0.0028. That ends up being, sorry about that, what? 0.5572. Okay. So at this point, now notice it does say express the solution in scientific notation. Scientific notation. So where does it have to be? It's got to be right there between the, 0.55 is too small. So I got to move it over. What? To 5.572 times 10 to the -1. Again, check it. Since it's 10 to the -1, that means I would move that thing back left 1 to get back to the 0.5572. I just realized that 7,200. That's not scientific notation. We need to put it right there between the 7 and the 2. Right now it's right here, 7,200. So move it over 1, 2, 3. Okay. Now with multiplication, you could do the same thing. The only problem is you're going to get in trouble sometimes if you got these really large numbers, especially with multiplication and division. So what I would do is I would use these rules. A to the n, the exponent rules, times a to the m times a to the n. That's an n as in nothing. It's a to the m plus n. And then your division property of exponents is a to the m over a to the n is a to the m minus n. Okay. So for instance, on this first one, what I'm going to do is I'm saying, well, all this stuff's being multiplied anyway, so I can multiply the 4.7 times the 3.2 first. And then I could take the 10 to the 6th and multiply it by 10 to the negative 2. Okay, and since these are both base 10, that's 6 plus the negative 2 on that, right? So I'm using this property right here. So 10 to the 4th. Then I go ahead and multiply 4.7 times 3.2. I'm just going to grab my calculator now. I'll go ahead and do that. 15.04 times 10 to the 4th. Now remember, we got to put this back into scientific notation. This 15, this is too big, right? That thing's got to be less than 10 and greater than or equal to 1. So we got to move it over. So when we move that, so 15.04 becomes 1.504 times 10 to the 1, and I've still got this 10 to the 4. So 1.504 times 10 to the 5th. Okay, so that'll end up being. So that second one there, I'm just going to run this one kind of like the last one. I'm going to go ahead because I'm like, well, I'm not going to be in trouble if I just go ahead and multiply those two, and then I'm just going to put that into scientific notation. So you end up with, if I multiply those two, I get 0.009324. And now I just got to make sure I put it where it needs to be between that 9 and the 3. So 9.3024, I move that 1, 2, 3 times. So negative 3, because you got to move it back left 3 to get back to where you were. Okay, so that's kind of what you want to think about on these ones. Similarly with the division, okay, so what I'm going to do here is I'm going to divide those two first. 9.62 divided by 3.28. And I get 2.93, 29268. Oh, this thing keeps going. 29268.3. Is times, now notice I got 10 to the 12 over 10 to the negative 1. So the rule is a to the m over a to the n, as you might recall, is a to the m minus n. Okay. So this will be times 10 to the 12 minus the negative 1. Well, 12 minus the negative 1 is 13. Okay. So now you got 2.93 blah blah blah, but luckily this part, right, is fine because it's greater than or equal to 1, but it's less than 3. So I'm just going to cut it off. Let's say we're rounding to the nearest thousandth or something. So I'm going to say 2.933 times 10 to the 13th on that one. Okay. On this one up here, I'm going to go ahead and do a similar approach, but with that one, I'm going to put that in scientific notation. So that's 3.85 times 10 to the, looks like I got to move that 1, 2, 3, 4, 5. 9.03 times 10 to the negative 7. Now I'm going to do those two, 3.85 divided by 9.03. And I get 0.426357. I'm going to round that. And then 10 to the negative 5 times 10 to the negative 7, so that'll be negative 5 minus the negative 7. So negative 5 plus 7 is 10 squared. Now notice this part. So I got 0.426357 times 10 squared. This is not big enough. Remember, I got to be bigger than 1, less than 7, so I got to move it over 1. 4.26357 times 10 to the negative 1. So I got to move it back left 1 to have that originally. I still got this 10 squared. Now I do those two back together, so negative 1 plus 2 is a 10. So this ends up being 4.26357 times 10 to the 1. It's 10 to the 1. Okay. All right, let's do an application here. We got the power dissipated by a resistor is the current, I, that's what they use for current, times the V voltage. Okay, so they're going to give you P, they want you to find the power here if the current, so there's our I, 3.75 times 10 to the negative 3. If you have this current in amps here, and then a voltage, V, 7.24 times 10 to the negative 4, is given. What would be the power? So I'm going to go 3.75 times 7.24. And I get 27.15. And then I got 10 to the negative 3 times 10 to the negative 4. So add up those exponents. 10 to the negative 7, negative 3 plus negative 4, negative 7. But this is too big, right? I got to be less than 10, greater than or equal to 1 on that. So I'm going to move that left one. So this will be 2.715 times 10 to the 1. I've still got this 10, negative 7. Now those two, 1 minus 7 is negative 6. So 2.715, whoops, times 10 to the negative 6. So I got to combine those two. And there we are. That's our power in scientific notation. All right, thanks for watching. We'll see you guys next time.